In this video, we are going to investigate applications for the first derivative of a function. And we'll start by defining what we call critical points, which are points on a function where its derivative equals 0 or its derivative does not exist or is undefined. We'll make a quick picture for an example to start with. A parabola that's defined as f of x equals x squared minus 2x plus 3. And one point to highlight is the vertex of this parabola. Recall that we can find the x-coordinate for that vertex by using opposite of b over 2a, our b and a values from this quadratic function, and we would get opposite of negative 2 over 2 times 1, which simplifies down to 1. At the same time, we're going to take a look at our first derivative for this function, which would be f prime equals 2x minus 2. And we're going to look for critical values using this function. The first thing we're going to look at is, when does the derivative equal 0? Which occurs when 2x minus 2 equals 0, or when x equals 1. Notice this is not a mistake. This is an exact match for the x-coordinate for our vertex. And for points where the derivative does not exist, we won't have any of those. This is a polynomial, so it's continuous for all real numbers. Now what I'm going to do is take this information and form a mini number line just for f prime, marking down all critical values on the number line. And what I'm going to use this for is to break down a couple things. First, just remember that f prime is the slope or the rate of change for a function. When f prime is greater than 0, our function is increasing. And when the derivative is less than 0, our original function is decreasing. Well, when do these two things happen? It's easy enough to see from the graph that to the left of our vertex, everything less than the x value of 1, the derivative for this function would be less than 0. It is decreasing over that interval. And to the right of the vertex, or for x values greater than 1, the derivative is positive. This function is increasing. And this critical point, why these are so important, is this was the only place where the sign could have possibly changed, and it did. Let's say we weren't looking at the graph, and we wanted a more analytical approach to figuring out where our function was increasing or decreasing. Well, if I use a value to the left of 1, something less like 0, and I plug that into the derivative, I would get a negative value, which means that every value less than 1 has to have a negative derivative. Similarly, if I pick something greater than 1, like 2, I'm going to get a positive derivative value, which means for all x values greater than 1, my derivative must be positive. There was no chance for me to change signs, which means our derivative was positive and our function was increasing on the interval 1 to infinity, and the derivative was negative and our function was decreasing from negative infinity up to 1. And the derivative changed signs from having negative values to positive values at x equals 1, where the derivative was 0, where our parabola had its vertex. More importantly, where this function has a minimum. If our function changes from decrease to increase, that is the definition of a minimum. And it lines up perfectly with where our derivative changes from negative to positive. And in the rest of this video, we are going to go about formalizing steps to analyzing a function using its first derivative. So let's use this example side by side with the steps I'm going to write out. Our example function, f of x equals x cubed minus 4x squared minus 3x plus 2. And if we're going to use the first derivative, our first step will be to evaluate the derivative. In this case, f prime of x equals 3x squared minus 8x minus 3. Step 2, we're going to find critical values for our function, where the derivative equals 0 and where the derivative does not exist. So we'll make a table to organize this, and starting with f prime equal to 0, we will set this quadratic function equal to 0, and let's see if we can factor that. So it does factor into 3x plus 1 times x minus 3, which would give us two solutions, x equals negative 1/3 and x equals 3. We will not have any points where the derivative does not exist. This is a polynomial, and it's defined for all real numbers. Step 3, we're going to give a name to the number line we set up back at the beginning of this video. We're going to create what's called a sign chart for f prime. And on this sign chart, or on this number line, we're going to place any critical values we have found. And in step 4, we're going to pick test values on all open intervals to determine the sign of the derivative. So for a value less than negative 1/3, we can use negative 1. Between negative 1/3 and 3, let's use 0. And for greater than 3, let's use 4. And we're going to substitute all of those into our derivative function. So plugging in negative 1, and I'm just going to plug it into the factored form we had from our table above, we would get a negative from the first term times a negative from the second term, and that will equal a positive, which means over that entire interval, the only possibility is that my derivative has to be positive. Plugging in 0, well, that would just be the y-intercept from the derivative, which would be negative 3, which means everything between negative 1/3 and 3 has to have negative values. And finally, we'll test out 4 in that factored form and see that we'll get a positive times a positive, or all positive values when x is greater than 3. And now we get to the first thing that we can analyze from the first derivative. We're going to state that all positive intervals for the derivative will be intervals where our original f function was increasing. And all negative intervals, those will be spots where our original function was decreasing. So here, the original f of x, we would say, must be increasing on the intervals negative infinity to negative 1/3 and from 3 to infinity, the same intervals where f prime was positive. And our f of x function was decreasing on the interval negative 1/3 to 3, the only interval where the derivative values had to be negative. And finally, we'll finish up with what's known as the first derivative test. And the first derivative test states that at any critical point, if the first derivative changes from positive to negative, the function f has a relative maximum at this point. If f prime changes from positive to negative, our function changed from increasing to decreasing, the definition of a relative maximum. And so it follows that if f prime changes from negative to positive, decreasing to increasing, then f has a relative minimum at this point. And if we see no sign change, that's inconclusive. There's not much we can say off of that. So to finish up, applying the first derivative test to our function, note from our sign chart that since f prime of negative 1/3 equals 0, and f prime changes from positive to negative at this point by the first derivative test, our function f has a relative maximum at x equals negative 1/3. And we had another sign change. So since f prime of 3 equals 0, and f prime changes from negative to positive at this point, f of x also has a relative minimum at x equals 3. And the only thing left for you to do is practice this type of analysis with a lot of different types of functions. Anything that to this point you have been able to find the derivative for. And thank you for watching.